We look at problem 2. All right, so we're good. Mean, median, mode. Mean and median, your calculator will tell you. The mode, it does not. That's just the one that shows up the most, so we can handle that. The range. If you look on your formula sheet, it tells you, I'm pretty sure it's on there, that range is?
It is. The largest minus the smallest.
Largest minus smallest. So, range, we just subtract our highest minus our lowest point. So that was back under chapter 3, like the third bullet down. So our highest value, looking back at our set of data, it's not the one that's listed first, it's the biggest number in my list. So that was 61 minus the smallest number in the list was, oh, I'm doing 1.
Yeah.
Why am I doing number 1?
I was.
Yeah, I was just, I don't know, not looking at question number 2, I guess.
This is the lower and upper.
Okay, let's go to question number 2. You guys are good with range, right?
Yeah.
All that question 1 stuff, that, I will tell you, like, pretty much the entire first page of the test is question number 1. Okay, all of those different things that we might do with the data set. So, number 2. So we found standard deviation from our calculator, the quartiles, explaining that. So D, upper and lower fence. So if we look at our formula sheet, you've got those definitions. Lower fence is quartile 1 minus 1.5 IQR. So if we look back at part B, quartile 1 is negative 0.005 minus 1.5, the IQR from question B is 0.09. So then we just plug that into our calculator. And we get negative 0.14. Upper fence, quartile 3 plus 1.5 IQR. So quartile 3 was 0.085 plus 1.5 times 0.9.
0.09.
0.09, thank you. And we get 0.22. So that tells us any number between those is okay. So for our outliers, look back at that original set at the beginning of number 2. Is there any number smaller than negative 0.14? No. Is there any number bigger than positive 0.22? And that was the 0.29. So that's why it's an outlier. So if you're smaller than the lower fence or bigger than the upper fence, it's an outlier. Is that okay? Alright, so number 3. You guys didn't ask about A, but I'm going to go over it anyway. So if we think about our data, oh, that is horrible. Pretend that's a bell shape. So I gave you this like whole handout of just bell graphs in case that helped you to draw them out. We know the mean is the middle here. So our mean was 101. And the standard deviation was 14. So if you want to find the first standard deviation, what do you have to do?
Add and subtract 14.
So one standard deviation, 101 plus 14 and 101 minus 14. So if you're between 87 and 115, that's one standard deviation. Okay, if you want the second standard deviation, you do it again. 115 plus 14 is 129. 87 minus 14 is 73. So that's 2 standard deviations. If you want 3, we just do it again. So 129 plus 14, give me 143. 73 minus 14 is 59. So if you're between those numbers, that's 3 standard deviations. Everybody understand that part? So part A says if it's bell-shaped. So if you look at your formula sheet, if it's bell-shaped, that's the empirical rule. And if we're between 87 and 115, that's the 1 standard deviation. So I look, my empirical rule, 1 standard deviation is 68% of our data. When I get to B, it says nothing is known about the shape. So now we're doing Chebyshev's, which is 1 minus 1 over k squared. We are between 59 and 143. So that is my 3 standard deviations. So that's the k. So it's 1 minus 1 over 3 squared. Okay, so if you type that in, you get 0.8 repeating. So that would be 88.89%. So if it tells you it's bell-shaped, it's empirical rule. If I don't know the shape, it has to be Chebyshev's. Is that okay?
Why is it not 9.7?
Because we don't know that it's bell-shaped. The empirical rule only works when I tell you that the data is bell-shaped. So here I said that. Here I said I don't know the shape, so I can't assume it's a bell. So that's when you use the other option. Alright, number 4. So this is like a weighted average. We've done some of these. Sometimes it's easier to think about than others. We've done some like with cost of things, like we did a trail mix or something one time. So this one is a GPA. I think we've had a couple like related to grades. So we know that we have all these scores, and it tells us each test is worth 20%. So my first test I got a 62, and the weight for that is 20. Did you guys do 20 or 0.2? Okay. You could technically do it either way. So we have to add together all of these values times their weights. So the next test was 83. It's also 20%. The next test was 91. It's also 20%. Then I have a term project of 88, and that project is worth 25%. And then we have homework of 76, which is worth 0.15. You divide by the sum of your weights. Okay, so if I add those together, we get 1. If you hadn't done the decimals, when you added your weights, you would have gotten 100. So you'd be dividing by 100, and it will give us the same thing. So then, if we calculate that, you get 80.60 divided by 1. So it's just an 80.6%. So when you're doing grades, you're essentially going to divide by that 100%. When we were doing like the trail mixes and those kinds of things, you can look, a lot of times those will say what's the cost per pound. So you know the pounds go on the bottom. So if it's something per something, if I give you those units, that tells you the last thing I mentioned is the denominator. So cost per pound, pound goes on the bottom. If I said dollars per ounce, the ounces go on the bottom. Something like that. Are there any questions there? Number 5. So we took 2 tests, geography and math, and I want to compare them. Okay. So I don't really know how to compare when I'm looking at 62 and a 261. Those aren't even percents. It's like telling me how many points I got on the test. And so that's not overly helpful unless we have a little more information. But it tells me, so on geography, my score was 62. On math it was 261. Geography had a mean of 80, standard deviation of 15. Math had a mean of 300, standard deviation of 26. So if you look, the only way to compare them is to get them in the same unit. That's a z-score. So if you're on your formula sheet, z-score, there's two, population and sample. Technically, it doesn't matter which one you use. We're going to get the same thing. It's R value minus the mean divided by standard deviation. So on geography, R score was 62 minus the mean of 80 divided by 15. Typically z-scores are 2 decimals, but if you give me more, there's nothing wrong with that. So we get negative 1.2 here. Math, R score was 261 minus the mean of 300 divided by our standard deviation of 26. And so if we calculate that, we get negative 1.5. So what these are telling us is how far you are from the mean. This is my mean, the class average. When these are negative, what does that tell me? You were below average, so you did worse than the class. So we're trying to decide which one of them was better. So neither one's great, but if I want the better option, which one is less below average?
Negative 1.2.
So I did better on my geography, because if you're thinking about these, here's negative 1.2, here's negative 1.5. This is the better one. Now, if those were positive numbers, if they were both positive, which one would have been better? The 1.5 would have been better in that case. So you do have to kind of think about it when you have those negatives there. Number 9. So you guys are okay with number 8? If you're trying to compare two sets, first look at the mean. If there's not a clear difference from the mean, look at the standard deviation. Do you want a bigger or a smaller standard deviation? Smaller is better. Smaller means more consistent. So smaller standard deviation is always what we're going to go for. On 9D. Okay, so on part C, you used your calculator and got this correlation coefficient. D, I told you to use table 2. So everybody pull out your table 2. All right, when we look at that, it has n and critical values. So if I look at this one, n is the number of points. How many points did I have in my data set? I think it was 7.
I'm not looking at it. Sorry. I thought it was fine.
So n was 7. So the critical value, if we're looking at an n of 7, is 0.754. So on the test, if I tell you to use table 2, I'm going to expect you to write down the critical value. If you don't, I'm going to assume that you really didn't look it up on the table. So please, if you're looking it up, write that down. Now what that tells me is if the absolute value of R is bigger than this, it's linear. Why do I do absolute value?
It's possible.
Yeah, because the critical value table only gives us positives. We know negatives in this case just mean the line is decreasing. So if we look, the absolute value of our R was bigger than the critical value, so that means it's linear. If the R is smaller than the critical value, it is not linear. Does that make sense to everyone? Like on part E, when I ask you to interpret the coefficient of determination, you guys can write me a sentence there. It's basically word for word from the formula sheet. It's just the percent of the variation that's explained by the regression line.
Can we say 96.1% of points fall on the line? Or do you want X is explained by? Or X explained by just never made sense to me.
Yeah, it doesn't necessarily mean they're exactly on the line.
Okay, I'll just explain.
Yeah, so here's why I have to be iffy about that, because when you only have a small number of points, it doesn't work out to be that way. Now, if we were looking at 1,000 points, it would turn out to be that way. So that's why it's a little bit iffy.
Explained by the line just makes sense to me.
Yeah.
It's like the line is just a made up line.
Right. It's basically because if you're on the line, you expect your y's to change, and so it's saying that the y's and our points are changing at that rate, essentially. All right. Let's see, so you guys can use your regression lines to make predictions, find your residuals. You guys are okay?
Yeah, can you go over I?
Yes, absolutely. So residual is observed minus predicted. Observed is like from the real data. Predicted is from our equation that we wrote. So we are looking at when x was 25. So when we're doing our residual, the real data, so if I look back up at my table, when my x was 25, the value was 67.5. Minus the predicted, so we did that on part H, we plugged 25 into our equation, and when we did that, we got 67.8321. So the first one's from the table, second one's by plugging it into our equation. So then when you subtract those, you get our residual. Negative 0.3321. Is that okay? So we were good with 10, deciding if something was significant or not. Talk about that a little bit. So 11. So we did x and standard deviation for both x and y on the calculator. You guys are okay with making that table for the correlation coefficient? I might ask you to do a very small data set on the test. I would probably only give you a few, 3 to 4 points if I'm asking you to do it by hand. But I will probably give you one, since I bothered to put a table on here. You can probably expect one on your test. So then part C, we are writing the equation. So if you look at your formula sheet. Alright, so if everybody goes back, it tells us the equation of the least squares regression line, y hat equals b sub 1x plus b sub 0. And it tells us b sub 1 is r times standard deviation of y divided by standard deviation of x. So if I want to find that, we go back. The r value from part B, now there is rounding error, so depending on how many decimals you kept, times standard deviation of y from our calculator on part A, divided by standard deviation of x on our calculator from part A. I started right at 4. Just trying to go from memory. That's not smart. Okay, so we plug those in. This is giving us our slope of 2.0233. So our equation, y hat, b sub 1 we just found, x plus, now we need that b sub 0. So if we look at our formula sheet, it tells us b sub 0 is y bar minus b sub 1 times x bar. So the mean for y from part A was 8.6 minus b sub 1 times the x bar from part A of 5.4. So this is really just a matter of being able to read those formulas and understand what they're asking us to do. So that's our y-intercept, so plus a negative, or you could put minus 0.325. So that is our regression. What else do you guys want to talk about? Standard deviation, yes. Okay, let me give us a set of data. I'm just going to make up some numbers. Okay, so if I give you these numbers, and we are computing standard deviation, we have to take each of our x's, subtract the mean, and square it. So first, we have to get what?
We have to get our standard deviation and our means for both x and y. Or I guess y.
Yeah, we only have one set, and we're finding the standard
Oh, I'm
deviation.
doing it wrong.
So let's assume this is a sample. So to get our mean, we can put them in the calculator, or we can just add them up and divide by 5. We get 22.2. So everybody know how I got that? So I'm just going to make a row for each of these x's. So I'm going to go through. So 13 minus 22.2. It's negative 9.2. And then you square it. It's 84.64. So we do this for each. So 17 minus 22.2. That's negative 5.2. Squared. 27.04. 25 minus 22.2. 2.8. Squared. 7.84. 6 gives us 3.8. Squared 14.44. 30 minus 22.2 is 7.8. Squared 60.84. Okay, if you're looking at your formula sheet, since this is a sample, it tells us standard deviation is the square root of the sum of xi minus x bar squared divided by n minus 1. So we have the square root. This means we add all those numbers up. You guys get 194.8? How do we do n minus 1?
And take up the sum of the number of terms you have minus 1.
Okay, so we have 5 terms, minus 1 is 4. So I'm just typing in the square root, 194.8 divided by 4. Okay, that's equals 6.9785. Other questions there? Anything else you guys want to go over for our test? So if your data is skewed, is mean or median better?
Median.
If data skewed, you want your median. If it's bell-shaped, we want the mean. If the data is bell-shaped, would standard deviation or interquartile range be better? Standard deviation. What do we call that when something changes a lot, when we have a really high slope? Resistant. So resistant would be like your median, your interquartile range. One big number doesn't change those a lot. Your mean, standard deviation, those are not resistant. They change.
Is that on here somewhere, or is that something I have to know?
I don't think the definition of resistant is on there, so we do have to know
But
that. one.
resistant means it changes a lot.
Yeah.
Which doesn't really make sense with the
It's what we say it's not resistant.
Okay.
So, you guys know how to find mean, median, mode. We can get more than one mode if you have multiple values that show up the same amount of times. Mode is just whatever shows up the most. Do you want a high or low standard deviation? Low. Lower standard deviation means more consistent. A variable that we didn't take into consideration is a lurking variable. Residual plots, what are the problems we can find with those? Yeah, when it's like getting wider over time, if we see a pattern, or if we have an outlier. You guys don't have any more questions, so that's all I've got for you.
Interesting. I need to watch this marker off my face.
So, you're welcome to